Hi, to everybody. In this lecture video, we are going to be doing chapter 29. And chapter 29 is about the magnetic fields. Now, after doing this chapter, you will be able to define a magnetic field, and you will also be able to derive an expression for the magnetic force exerted on a current carrying conductor, and you will also be able to derive an expression for the torque exerted on a current carrying loop, and you will also be able to discuss the motion of charged particles in magnetic field and obtain an expression for the cyclotron frequency. And you will also be able to discuss the Hall effect and its application. And you will also be expected to solve the problems on the above aspects. All right, let us just start by defining the magnetic poles. Now, every magnet, regardless of its shape, has two poles. Now, and these poles are called north and south pole. Poles exert the force on one another in a similar way that the electric charges exert the force on each other. That is, the like poles repel each other while the unlike poles attract each other. The force between two poles varies as the inverse square of the distance between them. A single magnetic pole has never been isolated. Now, this sentence means that there's no discovery or the monopole in terms of the magnetism has not been discovered yet. For an example, you cannot have just a north pole or a south pole. I just want to show you a piece of magnet here, like from your high school. You remember, if you have a piece of magnet just like that, it's always having a north and a south, and the magnetic field will always be carrying away from north to south. I will just draw only one. So this is how a magnetic poles are always. Now, even if you cut this magnet, say you cut it here, a very small piece of that magnet, and then I'm going to put that piece here that we've just cut there. Now, even on that piece, it means that you are always going to have north and south pole on this piece. And this is one of the experiments that everybody have done when we were still kids. Right. Now, unlike in the electric charges, because for electric charges, you can just have a positive charge as a standalone, and you can also have a negative charge as a standalone. And you still remember that the electric field will always be radiating away from the positive charge, and the electric field will always be radiating into the negative charge. So as far as the charges are concerned, you can have a monopole charge, or the only a negative charge or only a positive charge separated. But as far as the magnetism is concerned, you cannot have, or you cannot isolate a north to south pole. Even if you cut that magnet with the very smallest piece that you can cut, you will still have north and south. So believe it or not, good people, the existence of a monopole in terms of the magnetism has not been discovered, and people or group of people or researchers who are going to discover that, I'm pretty sure that they will get the Nobel Prize. So that's what this sentence is actually saying. That is, the existence of monopole has not been discovered yet. All right. Now, as a reminder, remember that an electric field surrounds any electric charge, as I've just shown you. Now, the region of a space surrounding any moving electric charge also contains a magnetic field. I just want to repeat that. A region of space surrounding any moving electric charge also contains a magnetic field. Therefore, the magnetic field will always exist when these charges are moving. But when they are not moving, magnetic field cannot exist. Only when these charges are moving. The magnetic field also surrounds a magnetic substance, making up a permanent magnet, as I've shown you in the whiteboard. Now, and the magnetic field is a vector quantity, and then we are using a symbol B to actually denote the magnetic field B, like we are using E to denote the electric field. What I'm just trying to say here is the magnetic field is denoted by this alphabet B, while the electric field was denoted by this letter E. Therefore, the electric force was denoted by F subscript E. Therefore, the magnetic force will also be denoted by F subscript B. This is the magnetic force, this is the electric force. Right. Now, the symbol that we are using for the magnetic field is just B. Now, the direction is given by the direction of a north pole of a compass needle pointing in that location. Magnetic field lines can also be used to show how the field as traced out by a compass will look like. For an example, as I've shown you that the magnetic field will always be pointing from north to the south pole. Magnetic field will always be pointing from north to the south pole. The compass can be used to trace the field lines. For example, the compass will always be pointing to the direction of the magnetic field. Will always be pointing from north to the south. The moment you put the compass in this region, it will just be pointing at the direction of where the magnetic field is going at that location. But when you put it here, it will also be pointing the direction of magnetic field at that location. Right. Now, the magnetic field at some point in space can be defined in terms of the magnetic force. As I've already explained, that the magnetic force is just given by that F subscript B, while the electric field is given by F subscript E. The magnetic force will be exerted on a charged particle moving with a velocity v. For now, I will want you to assume that there are no gravitational and electric field present for now, from now onwards. And then I will also tell you when you just have to assume that the electric fields are also present. For this part of this chapter, I want you to just assume so that we can be able to deal with only the magnetic field. Just assume that the only magnetic field exist or are present on these charged particles. Right. Now that force is given by this F cross B is given by that, where F is just a force and Q is just a charge and V is your velocity, B is the magnetic field. Now the magnetic force is just given by that equation. The FB is just given by Q V cross B. Now, this is a cross product of two vectors. I just want to remind you the fact that the cross product of two vectors is always a vector, because this can just be defined in terms of the magnitude of A times the magnitude of B and the sine of an angle between them. Now, for the magnetic force, obviously, this is just going to be equivalent to Q V. All right, sorry. Just want to write it afresh somewhere here. Now, the magnetic force in that case, the magnitude of the magnetic force will therefore be given as QVB, the magnitude of the magnetic field, the sine of an angle between them. Right. I also want to remind you what is the sine graph. Sine graph is drawn like this. That is a sine graph, where here is 2 pi, and then here you have pi, and there you've got 0, and then here you have half pi or 90 degrees, and then here you have 3 pi halves. Right. So that is the cross product of two vectors, and the cross product of two vectors is always a vector. For an example, I also want to show you that if you have, say, a certain vector A pointing in this direction. Say a certain vector A is pointing in that direction, vector A is pointing in that direction, and you also have a vector B pointing in this direction here. Now you know the angle between them. Now in this case, when I am saying A cross B, when I'm saying A cross B, when I'm saying A cross B, the direction of A cross B, it will just be the shortest distance from A to B when I'm using my right-hand rule. The shortest distance from A to B. Therefore, that vector direction will be into the board. Now, we normally denote the vector going into the board by a circle with an X. But when I say B cross A, B cross A will be the shortest distance from vector B to A. Therefore, B cross A would be out of the board, and we normally denote the direction of the vector going out of the board to be like that. So these are some of the things that I also wanted to remind you in terms of the cross product of two vectors. Right. For an example, in this case, I suppose that you have the B field in this direction, and then you have a positive charge. Now, in that case, the magnetic field will always be in that direction, because the magnetic force is always perpendicular to the magnetic field and the velocity. Right. In this case, when you have a positive charge, the magnetic field, this is my magnetic field, and then this is the velocity of these charged particles, and this is my magnetic force. For an example, when you take this positive charge here in the region of magnetic field B, now that will be that the velocity is going up, but the magnetic field is going in that direction. So do you see this is the charged particles is going up, but the magnetic force, the magnetic field is going that direction. Therefore, the magnetic force must be on that direction. Now, when it is a negative charge, the direction will just be negative. It will just be coming this side as you are seeing it in this diagram, right? Now, as I've already explained to you, this is what we are going to use. This is the right-hand rule. This is the magnetic force, and then this is the velocity of this charged particle, and then this is the magnetic field. You will always have to use this right-hand rule in order to be able to know the direction of the force, right? Good. The magnitude of the magnetic force is just given by this. This is the sign of an angle because it's a cross product of B cross B. Now, in that case, I also wanted to show you once again that if the magnetic force is given as the magnitude of Q, magnitude of V, magnitude of B, the sign of an angle between them. Now, I just want to draw the sign graph here. The sign graph is drawn in this way, and then you've got 2 pi there, and then you've got 3 pi halves. At that point here you've got pi, and then here you've got pi half. Now in that case, I just want you to see that because this theta, remember, this theta is just an angle between, the velocity, the vector velocity, and then the vector B field, the magnetic field. And then this is the angle theta. And the magnetic force will always be perpendicular to both velocity and the magnetic field. So now in this case, do you see now, if the magnetic force is zero when the field are parallel or anti-parallel. When the field is parallel or anti-parallel to the velocity, do you see now that angle is just going to be zero? It's just going to be zero, and the sign of zero is zero, or it will just be, when they are anti-parallel, it will just be pi. It will just be zero. But you can have the maximum magnetic field when theta is equals to 90, because the sign of 90 is just given as 1. So that's what I wanted to show you, or to remind you of the sign graph. All right. Now let us also compare the differences between the electric and magnetic force. For an example, the electric force vector always is in the direction of the magnetic field, but the magnetic force vector is always perpendicular to the magnetic field, as I've just shown you, that the magnetic force is always perpendicular to the B field. Right. Now the electric force acts on the charged particles regardless whether the particle is moving, but the magnetic force acts on charged particles only when these charged particles are in motion. Now the electric force does work in displacing a charged particles, but the magnetic force associated with a steady magnetic field does no work when this particles is displaced. Force is always perpendicular to the displacement of a point of application. For an example, let me just remind you the definition of the work done. The work done is always given as F dot D. F dot D. Now you remember the dot product of two vectors is always a scalar. Now in that case, this is just the magnitude of force multiplied by the magnitude of the displacement, and that must be a cosine of an angle between them. Right. Now when we are talking about the work done by the magnetic force, that will be the FB, of course. That will be the FB, of course. That will be the FB. Right. Now, when you plot the cosine graph, you still remember that the cosine graph can be thrown in this way. This is my cosine graph, where here I have 2 pi, and then this point here is 3 pi halves, and then here I have pi, here I have pi halves. Now, when the magnetic force is always perpendicular, this is FB. FB is always perpendicular to the velocity, to this velocity of these charged particles, and then here you've got the magnetic field B. So because the magnetic force is always perpendicular to the velocity, and the angle between them is just 90, and the cos of 90 is just 0. As a result, the cos of 90 is just 0. Therefore, the magnetic force does no work. So I'm just trying to elaborate this last statement there. Right. The kinetic energy, therefore, because the magnetic force does no work, the kinetic energy of the charged particles moving through a magnetic field cannot be altered by the magnetic field alone. When a charged particles moves with a given velocity through a magnetic field, the field can be altered, the direction of the velocity, but not the speed of the kinetic energy, right? Because the magnetic force does no work. Right, now the SIU units of the magnetic field B is given as Tesla, and Tesla is just Weber divided by meter squared, and Weber divided by meters. Weber per meter squared is nothing else but it's just newtons per ampere per meter. And in some other books, the non-SIU units called Gauss for the magnetic field is also being used, and 1 Tesla is equals to 10 to the power 4 for Gauss. Now let us also do the following quick quiz. And electrons move in a plane of this screen towards the top of the screen. Therefore, the electron is moving up, and then the magnetic field is also in a plane of this screen and directed to the right. Therefore, remember the right-hand rule. This is the velocity of the charged particles, this is the magnetic force, and this is the B field. But in this case, the electron is moving up, but the magnetic field is towards the right. The magnetic field is towards the right. Therefore, if it was a proton, it was going to be into the screen. But because it is now an electron, therefore, the electron is going to have an opposite direction to the proton. Therefore, the electron will just be out of the screen. So as a result, the answer for that quick quiz is just E out of the screen, because that is an electron, not a proton. Right. Now let us also do the following quick example. An electron moving in a magnetic field. An electron moves through a space as a cosmic ray with a speed of 8.0 times 10 to the power 6 meters per second along the x-axis as shown in the diagram, and its location. The magnetic field of the Earth has a magnitude 0.5050 millitesla 10 to the power minus 3. This is a prefix and is directed at an angle of 60 degrees. The x-axis lying in the xy plane. Calculate the magnetic force on the electron. We know that the magnitude of the magnetic force is just QVB, the sign of an angle. Now, if you plug all the values, because you know the charge of an electron, this is what you are going to have as your magnetic force. Right. So the magnetic force will just be 5.5 multiplied by 10 to the power minus 7 Newton. Now, this is how we normally denote the vector. If the vector is out of the page, we denote it by the dot, and if the vector is out of the page, we denote it by the cross. As I've already shown you that, say you have two vectors, say you have vector A going in that direction, this is my vector A, say you also have another vector going in that direction, and if that is my vector B, and you know the angle between them, angle is theta. Therefore, when I am saying A cross B, vector A cross vector B, vector A cross vector B, the shortest distance from A to B, therefore that vector, the thumb is also always going to show us the direction of that vector, which is being made by A cross B, because A cross B can be another vector, say a vector C. So A cross B is just into the board. So as a result, when that vector is going into the board, we normally denote it by a circle with a cross, But if we say B cross A, B cross A will just be the shortest distance from vector B to A. That will be that vector which is going to go out of the board, and we denote it by a circle with a dot. Right. I just want to remind you the stuff that you have already done in your first semester. Right. Now, the B into the page is just this, and then the B out of the page is just denoted by those dots. Now, I just want to show you the movement of the charged particles in the region of the magnetic field, and for me to do that, I would like to just go to one of my simulation and show you how this will just be moving, and just want to show you the simulation of these charged particles. Yes, this is the simulation of this a positive charge moving in a region of the magnetic field. Do you see that is the velocity? The red is the velocity, but the blue is always the force, and the B is actually going into the board. Now, if you use the right-hand rule, the B is going into the board. For example, if this particle is at that point, is going up, now the magnetic force is always towards the center. Now, I also want to change the charge. Say this charge was negative. Now, if the charge is negative, it's going to be moving in the opposite direction to the positive charge. I also want to show you what will happen if, but what I want you to see is the fact that the force is always towards the center. Therefore, if I want to make it a neutral particle, that is a neutron is not going to be influenced by any electric field or magnetic field. Right. I just want to go back to the slides. Right. I am now back to the slides, and I just want to show you that when this particle is here, for example, the force, the particle is going up, the magnetic field is into the board, therefore the magnetic force is just going to be in this direction. I just want to repeat it once and for the last time. For the right-hand rule, like this is the velocity of charged particle, and this is the magnetic force, and this is the magnetic field. So if the B is into the board, I'm just talking about this charged particle at that point. Therefore, the velocity is going up, but the magnetic field is into the board, and this is the magnetic force. And as you can see, the magnetic force is always towards the center. Now, because this charged particle is moving in a circular, in this circle, it's just moving in this circle. Therefore, we can be able to determine the radius of that circle, because if we have assumed that the only magnetic force is the force that is acting, therefore that force must always be equivalent to the centripetal force of this. And then from that, because we know what is a centripetal force, and then we can be able to write the radius of that circle. The radius of that circle is just going to be given by m by the momentum divided by qb. That is, the radius is directly proportional to the momentum, or to the linear momentum of this charged particle, and it is inversely proportional to the magnetic field B. Right. Now, just because we know that this particle is moving in the angular, is moving with an angular velocity, and there's a relationship between the angular velocity and the linear velocity, as you know from your first semester, that V is given as omega r. The magnitude of the velocity is just given as omega r. Then omega r is just going to be given by this equation there. Now you can eventually be able to show that the angular frequency is just given as qb divided by m. Now that angular speed is normally referred as the cyclotron frequency. Now, because we know the angular velocity, we can therefore also be able to calculate the period of the motion to complete one second. Therefore, we know what is the velocity. We can just substitute the value for the velocity. Then, therefore, the period is just given by 2 pi m time divided by qb. All right. Sorry. Right, let us also do the following quick quiz. Now, this quick quiz states that a charged particle is moving perpendicular to the magnetic field in a circle with a radius r. An identical particle enters the field with velocity v perpendicular to b, but with a higher speed than the first particle. Compare with the radiuses of the circles for the first particle. Is the radius of the circular path for the second particles smaller, larger, or equal? Therefore, the answer for that must just be B. It must be larger. Just want to remind you again that the magnetic force, you remember the magnetic force, the magnitude of magnetic force is just given as QVB, and that must just be equal to the centripetal force. The centripetal force of, no, that must be divided by R. That must just be divided by R, not R squared. That must be just divided by R. Therefore, this velocity will cancel 1 here. And now, as a result, when you want to write the equation for R, the R is just going to be equals to, is directly proportional to the momentum divided by QB. As a result, when the velocity is big, therefore, because R is directly proportional to the velocity, and R is inversely proportional to, say, a magnetic field B. Therefore, if the speed is higher, the answer for that must just be B. Therefore, the answer for that will just be B. The radius will be larger when the velocity of the second particle is larger. Let us also do the second part of the quick quiz. A charged particle is moving perpendicular to the magnetic field in a circle with the radius r. The magnitude of the magnetic field is increased. Now, if the magnitude of the magnetic field is increased, compare the radius of the new circular path of the first particle with the radius of its initial path. Now, if you increase the magnetic field, the radius will always be decreasing. As a result, the answer for that must just be A. The radius for the second particle will just be smaller. Right. Now, I also want to show you that when this particle is moving at a certain, if this charged particles moves in a magnetic field at some arbitrary angle with respect to the magnetic field, its path is just a helix. It's just going to be moving in helix-like or helical path like this. But now when you are standing at the x-axis, when you are standing at x-axis, you are looking this motion from the x-axis. What you are going to see, you are just going to see the circle. Now, from that equation, the velocity in this case, because we have this is in y-x plane, you are just going to substitute the velocity with the velocity perpendicular, and the velocity perpendicular is nothing else but it's just the square root of vy squared plus vz squared. Right. When you are standing in the x-axis, you are just going to see the circles. Right. Now let us also do the following example of a proton moving perpendicular to a uniform magnetic field. A proton is moving in a circular orbit of radius 14 centimeter in a uniform magnetic field of 0.35 Tesla, perpendicular to the velocity of the proton. Find the speed of the proton. Right, sorry. Now, in this case, we know what is the velocity. The velocity is just given by that equation, and now you can just plug the values, and then you will be able to find the speed of the proton as 4.7 times 10 to the power minus 6 meters per second. Right, let us also do this bending, an example of a bending an electron in a beam. Now, in an experimental design to measure the magnitude of a uniform magnetic field, electrons are accelerated from rest through a potential difference of 350 volts and then enters a uniform region of magnetic field that is perpendicular to the velocity vector of the electrons. The electrons travel along a curved path because of the magnetic force exerted on them, and the radius of the path is just given as 7.5 centimeter. Such a curved beam of electrons is shown in the figure. Now, in this case, you are just going to have to see that cycle is just like in that helical movement. When you are standing in the x-axis, this is what you are going to see as a cycle. Now, in this case, when you solve the problem, because the electron is moving from rest, you just have to use the theorem of the kinetic, the conservation of energy. And when you substitute because you are looking for the velocity and you know what is the change in the change in the potential energy is just given as q times the change in the potential difference. Because you are given the change in potential difference, this is zero because the electron starts from rest. Now, when you make v a subject of the formula, this is what you are going to have. And when you substitute the values, you will get 1.1 times 10 to the power 7 meters per second. But the question was asking us to get the magnetic field. Now we know the mass of an electron, we know the velocity from the previous answer, then we know the charge, and then we are given the radius. Now, if you plug the values, you will get the magnetic field as 8.4 times 10 to the power minus 4. Right. Now, the second part of the question is asking you to get the angular speed of the electrons, because we already calculate the linear speed, the velocity v. Therefore, we know the radius. We can be able to get the angular velocity because the angular velocity is just given as v divided by r. And then you know the radius. The radius was given in the question. Therefore, the angular speed is just 1.5 times 10 to the power 8 rads per second. Now, when you've been asked to get this speed or this angular velocity in terms of revolution per second, therefore, in terms of the revolution per second, this is just going to be 2.4 times 10 to the power 7. I hope you are still able to convert the rest per second to the revolution per second from your first semester. You just divide the answer by 2 pi r rads. Therefore, that is just going to give you revolutions per second. Now, let us also talk about the charged particles moving in the electric and magnetic field. Now, you remember for the first part of this, I only told you that you must just assume that only these charged particles are experiencing the magnetic field. But now, in the real life, they will also be experiencing the electric field, V. These charged particles will just be moving in both a magnetic field and as well as the electric field. Now, in that case, the total force is therefore the algebraic sum of the electric force plus the magnetic force. This is what you are going to get in when you calculate the force. Right. So for an example, this is what you are going to have when you have this particle moving. This is your B. Your B field is into the board because I am seeing the X there, and then the electric field is in this direction. I just want to show you the simulations for this so that you can see what is going to happen. But what I can just also say is the fact that when you have the magnetic force, if the magnetic force is exactly equals to the electric force, therefore this particle will just move, that charged particle will just move through without any without being diverted to the left or to the right. But if the magnetic force is greater than the electric force, therefore the particle will be diverted to the left. But if the electric force is greater than the magnetic force, therefore the particle will just be deflected to the right. Right. Let me just get my simulation for this. I just want to show you the simulation for these charged particles moving in both region of the B as well as the in moving in the region of the both magnetic field as well as the electric field. Right, I just wanna launch this particle, but before I do that, yes, I mean, this is the speed of the particle and the particle is positive. Now, if I launch the particle, this is what is going to happen. Now, you see, this particle is just going to go up, is just going to be diverted up. It's just because there's imbalance between the magnetic force as well as the electric force. Now, I just want to check whether I can be able to change the charge on my particle. Let me just see. I cannot be able to change the charge in my particle, right? But just for the sake of this, I just want to show you that and engineers and the physicists can actually be able to steer this movement of this charged particle. For example, when the particles enters that region, they can even steer to change its direction by just varying the magnetic field B. Yes, so what I'm trying to say is this particle can just move directly to that without any deflection, only if the magnitude of the magnetic force and the electric force are the same. Right, I just want to go back to the slides. Yes, I'm now back to the slides. Right, yes, that's what I wanted to show you, that this particle can just move without being deflected when the magnetic force and the electric force are equal. Right, when the force due to electric force is equal but opposite to the force due to the magnetic field, the particle moves in the straight line. This occurs for velocities of the values. Now, I'm just going to equate the electric force to the magnetic force, and then from that you can just see Q will cancel the Q. Therefore, that velocity, that those particles must be moving at that specific velocity if the velocity is the ratio of the electric field to the magnetic field. Therefore, those particles will just be moving straight without any deflection in that region. Right, now, for the velocity selector, that is actually the velocity selector. So that is only particles with that velocity of the ratio of the electric field to the magnetic field are those particles which will just pass through these two fields without being deflected. All right, the magnetic force exerted on the particles moving at the speed greater than this is stronger than the electric field, and the particles will be deflected to the left, as I've already explained. Those moving more slowly will be deflected to the right. Right. Let me also show you the mass meter simulation. In this case, a mass spectrometer separates ions according to their mass to charge ratio. A beam of ions pass through a velocity selector. You remember this is a velocity selector. When we have the magnetic field B as well as the electric field, and these particles are moving at that speed, only particles with that speed, which will be equivalent to the ratio of the electric field to the magnetic field, will only be able to pass through without being deflected. Now, when we reach the second part of the magnetic field, these particles, depending on whether it's positive or negatively charged, it will just be making this semicircle to the other side. And then when you place the detector at point P, you can actually be able to determine the ion, which ion is that. I also want to show you the simulation for this situation. Right. Let me just get it right. The simulation for this. No, that's not the one. This. Yes, this is the simulation for this one. I'm just gonna launch my positive charge in this with moving at a certain speed. Now, when I launch that, this particle is just going to move straight without being deflected. But when it reaches this region of the magnetic field, it will just make a semi second. Right. I can also be able to vary the magnetic field. You see, I mean, I can vary the magnetic field. You see, when I'm varying the magnetic field is out of the board, then I can reset and then launch the particle and then see what is going to happen to that particle. Right, sorry. If the particle is positive, it's going to be deflected up. But what if the particle was just a negatively charged particle? Just want to change and make it negatively charged particle. Sorry, just want to make it negatively charged particles. Now I can launch and then see what is going to happen. And if that particle is negatively charged, let us just see what is going to happen. But in this case, I also want to show you that the magnetic field in this case is into the board. Now let us just see what is going to happen when we reach this second region of the magnetic field. Now, do you see the particle is just going to be deflected down? The particle is just going to be deflected down. But if the particle was positively charged, it was going to be deflected up. So that's what I wanted to show you. Right. Let me just go back to the slides. Just want to go back to the slides. Yes. I'm just back to the slides now. Right. So that's what I wanted to show you. Now, if we calculate the mass the mass to charge ratio, this is what is going to be given by this equation. But we already know what is the velocity. The velocity is the ratio of the electric field to the magnetic field at that region. Therefore, when we plug this to this equation, this is what you are going to have. The mass to charge ratio is just given by this equation, where this P is the magnetic field in this region and the P naught is the magnetic field in the second region. Right. Now, after entering the second magnetic field, the ions move in a semicircle of radius r before striking a detector at point P. If the ions are positively charged, they deflect to the left, and if the ions are negatively charged, they deflect to the right. As a result, as you can see, now this is very important because we can be able to separate the positive ions to the negative ions just by putting the magnetic field as well as the electric field, because it will definitely separate the positive charge to the negatively charged ions. Right. Now let us also talk about the cyclotron. A cyclotron is a device that can accelerate the charged particles to a very high speed. The energetic particles produced are used to bombard atomic nuclei and thereby produce the reaction. Now, this reaction can be analyzed by the nuclear physicists or nuclear engineers, so that they can actually study the structure of a nucleus of this particle. Now, in this case, this is what you are going to have. The cyclotron is made with these are called these because of their shapes. A high frequency alternating potential difference is applied to the these. A uniform magnetic field is perpendicular to them. In that case, a positive ion is released near the center and moves in a semi-path. The potential difference is adjusted so that the polarity of the D is reversed in the same time interval as the particle travel around 1D. This ensures that the kinetic energy of the particles increases in each trip. Now, in that case, the kinetic energy of this particle is given by that, but we already know what is the velocity. If you plug the velocity in that equation, this is what you are going to have as a kinetic energy of this particle. Now, that kinetic energy doesn't depend on the velocity. But however, I also want to mention that when the energy of these ions is in a cyclotron exceeds about 20 mega electron volts, therefore the relativistic effects came into account. They need to be taken into account. Now, the magnetic force on the current carrying conductor. A force is exerted on the current carrying conductor placed in the magnetic field. The current is a collection of many charge moving in say one direction. Now the direction of the force is given by the right hand rule. By the right hand rule. The right hand rule is just the direction of the magnetic force. The magnetic force is this one. The B field is in this direction. Then this is your speed of, this is the motion, the direction of the velocity of this charged particles. Right. Now, for example, let us just put this wire inside the region of the magnetic field. The B field is into the board. Now, there's no current on the wire, therefore there's no motion on the wire. However, if we send current up, we are sending current up and the magnetic field is into the board. You see, the magnetic field is into the board. Now the current is, the charged particles are moving up, therefore the magnetic force will deflect the wire to the right. Now suppose that I change the direction of the current. It is not going up, now it's going down. If the current is going down, therefore the magnetic field is into the board. Now the current is going down, the charged particles are going down, therefore I will just have to turn my hand to be like that. Now in that case, the magnetic force will just be deflecting the wire to the right. Good. Now in this case, we know what is the magnetic force, and if we take that velocity as a drift velocity of these charged particles, this is what we are going to have as the equation for the magnetic force is Q multiplied by the drift velocity cross the magnetic field B. Now the total force is the product of the force on one charge and the number of these charges. From the previous chapters, you can just be able to see that. I will just have to multiply this by the number of charges passing through that volume, where L is just the length of the wire, and this area is the cross-sectional area in that wire. Now this, I can just write that in terms of the current. Now if I want to write that in terms of the current, this is what I'm going to have. Now the magnetic force is just given by the current L cross B, where I is the current and the L is the vector that points in the direction of the current. Now the B is just the magnitude of the B field, and that L, its magnitude is just the length of the segment. Right. Now, but for the just consider the segment of a wire, this wire, and then I'm just going to take ds, a small portion of this displacement of these charged particles in, and this wire is being placed in the region of the magnetic field B. Now in that case, the force, the small amount of force, if I'm taking that small displacement of this wire, therefore it will just be I, the small displacement ds cross B. Now the total force will, therefore I will just have to use the integration. If I'm moving from A to B, that will just be I in the integral, because I is the current, which is just constant. I can take it outside the integral, and then I integrate ds cross B. Remember, ds cross B will always be in the different direction compared to to DS and B. Therefore, the force will always be in a different direction. For example, if the magnetic field is in this direction and the DS is in that direction, the force will just be will always be perpendicular to DS and the magnetic field. With that, I think we are ready to be doing the following quick quiz. A wire carries a current in the plane of this screen towards the top. Towards the top, the wire experiences a magnetic force towards the right edge of the screen. Is the direction of the magnetic field causing? Now, this is the wire is carrying current up the screen, and the wire experiences a magnetic force. The magnetic force towards the right. Therefore, the magnetic force is this, but it is towards the right. Therefore, the magnetic force is towards the right. Now, what is the direction of the B field? The B field. The B field is this. The B field will just be out of the screen or out of the board. Right. You will always have to use that, and I've just shown you how to get the right answer in that case, because this is going up and then the force is towards the right. Therefore, the B field must just be out of the board. Now, let us just use the previous integration that we have, the integral equation that we have derived to actually calculate the force on the semicircular conductor. A wire bent in a semicircle of a radius r forms a closed circuit and carries a current I. The wire lies in the XY plane and a uniform magnetic field as shown is directed along the positive y-axis. Find the magnitude and the direction of the magnetic force acting on the straight portion of the wire and on the curved portion. Now, we want to get the magnetic field through this portion, and then we also through this portion, and we also want to get the magnetic field through the KV surface. Now, in order for us to do that, let us just start with this flat surface of this wire. In that case, I just want to make it a point that you see in that case I have the I cross the DS cross B. The DS in this case, I'm just going to have the DS in the x-axis. That is why now DS is nothing else but it just becomes DS. It just becomes DS. It just becomes DS. Now, when I am taking DS cross B, because the magnetic field is going up, DS cross B is just going to be out of the board. Now, I'm going to take that direction of the out of the board to be positive. If now that is positive, and I'm just taking the integral because I'm moving from R to minus R, because when I am moving from here to there, this is R, but when I'm moving from there to there, it's minus R. Now I integrate from R to minus R, and then the magnitude of B and DS is nothing else but is DS. Look at the direction. The direction of the force is just going to be in K direction when the DS is in I and the magnetic field is in J. That is, I cross J is always in K. Right. Now, when you do that integral, this is what you are going to have. Now, in this case, this is very simple because the integral, force, the force is just given by this integral here. I just want to do it very quick. The force is just given by that integral. The B is just constant. You can just take it outside the integral I. That is going to be IB. Now, the integral of the integral dx is nothing else but it's just x. And then for you put minus r, you also put r there. And when you work out this, you just see that this is just 2 because it's r minus r. That will be 2r. Therefore, when you plug that, this is what you are going to have. And that is for that flat surface of the wire. Right. Now let us also do this for the KV surface of this wire, for the KV surface of this wire. Now for the KV surface of this wire, I am still using the same equation there, but this is just going to be minus because I'm just going to take the DS cross B. DS cross B, the shortest distance from DS to B is just into the board. Now, if I've taken the one out of the board as positive, the one into the board must be negative. That is why you are seeing this minus sign here. But ds cross b is just the magnitude of ds and the magnitude of b, the sign of an angle between them. But what is ds? Now, the ds from this triangle is just given by r d theta. Now, in that case, this is what I'm just going to have when I plug things back to the equation. And in this case, I'm just integrating with respect to d theta, and theta is moving from 0 to pi. That's why the integral is moving from 0 to pi, and this minus is actually coming from there, because ds cross b is into the board, and if I have taken out of the board as positive, the one for into the board must therefore be negative. Otherwise, I can also take them vice versa. If I am taking them vice versa, this one will be negative, while this one will just be positive. Right. Now, in that case, when you integrate that, everything is just constant there. You can take them outside the integral. Then you just integrate the sign of theta d theta. Now, when you integrate this, the sign is just going to be minus cos. And then if you put the integration limits, this is what you are going to have. Now, the total force, therefore, will just be F1 plus F2. Now, it is just going to give us 0. That will tell us that there is no magnetic force when the B field is uniform. Right. Good. Right. Let us also do the talk on the current carrying loop. In this case, you have this rectangular loop. You have this rectangular loop, and the B field is sent in this direction. The rectangular loop carries a current I in the uniform magnetic field. No magnetic force acts on side 1 and side 3. On side 1 and side 3, there's no magnetic force. Why? Is because the magnetic force, remember the equation for the magnetic force in this case, the magnetic force is nothing else but it's just IL cross B. Now, this is nothing else but it's just IL magnitude of B, the sine of an angle theta. Now, for region 1 and 2, what is the angle between L and B? They are parallel or anti-parallel. Now, what is the sine of 0? What is the sine of 180? It's just 0. Therefore, this is just going to give us 0. The wires are parallel to this. L cross B will just be 0 because of a sine between the sine of theta between the L and B. Right. Now, we are only going to be calculating the force on this region 2 and then region 4, which is this side and that side. And the current here is going down, while the current on the other side is going up. Right. Now, in that case, there is a force on side 2 and side 4 since they are perpendicular to the field. And that is actually the maximum force because they are perpendicular to the field. And the sine of 90 degrees is actually a maximum, or is just equals to 1. Now, in that case, the magnitude of the force, the magnetic force on these sides will just be given by this equation here. That is just going to be I times AB. Why AB? Because we know what is A. A is just that length, that L. And the sine of 90 degrees is just 1. Right. But what is very important is the direction of the force is out of the page. The direction of the force is out of the page for the F2 because the current is going down. You see, you've got the magnetic field. The current is going down. The magnetic field is in that direction. The current is going down. Therefore, it's out of the page. This is the B field and then the velocity of the charged particles. But for the region number 4, now the current is going up. The magnetic field is going on that direction. This is a B field. The current, the charged particles are moving up. Therefore, the current must be into the page or into the port. Right. Good. The talk on the current carrying loop, the forces are equal and in an opposite direction, but not along the same line of action. Now, in that case, there will be a force F2 and there will also be a force F for going down. Now, the force produces a torque around point O. If we have point O here, there will be a torque that is going to be produced by this force. Now, in that case, what is a torque? A torque is just the force times the distance, and then we know the distance at point O, because we know it is just going to be b half. And then when you add the b half plus that, because we know that the force is just the same, therefore this will just add algebraical, and then you are just going to have the maximum torque is A times B, and A times B is nothing else but this is just the area of that loop, and this B, big B, is nothing else but it's just the magnetic field. Right, now the area enclosed by the loop is just now if we want to define the maximum torque in terms of the area, therefore AB will just be the area, and then therefore the maximum torque is just given by I times A times B. Therefore this maximum value occurs only when the field is parallel to the plane of the loop. Right, now in that case, assume the magnetic field makes an angle of theta, which is less than 90 with the line perpendicular to the plane of the loop. The net torque about a point O will just be given by this equation. The maximum torque is just going to be IAB, the sine of an angle theta, the sine of an angle theta. Why an angle theta? Because if we want to write it in a vector form, this is what we are going to have in a vector form, that the torque is nothing else but it's just the current times vector A cross B. Now, if we want to write the magnitudes of this is just going to be a torque. It's just given as the magnitude of current, magnitude of the area, times B, the sine of an angle between them. Is a cross product of two vectors. It's just the sine of an angle between them. So that's that equation that you are seeing here. It must be multiplied by the sine of an angle of theta. Right. Now the torque has a maximum value when the field is perpendicular to the normal to the plane of the loop. Why is normal? Because the theta, the angle between the vector area as well as the B is 90, and the sine of 90 is just a maximum. The torque is 0 when the field is parallel to the normal to the plane or antiparallel. So in that case, you are just going to have 0 because the parallel or antiparallel vectors, the angle between them is 0 or 180. Now the torque is just given by that, and then the A vector is perpendicular to the plane of the loop and has a magnitude equal to the area of that loop. Right, now in terms of the directions, this is what you are going to have. The area is just going to be that vector pointing in that direction, and then the current is just going to be flowing around that loop, while the magnetic moment is pointing up, and that vector area is pointing in the same direction as that vector area A. Now, the product IA is defined as the magnetic dipole moment, or the magnetic moment, which is just mu. Now, in that case, the torque can just be given in terms of this equation here, because IA is nothing else but it's just the magnetic moment or the magnetic dipole moment. And the SI units of the magnetic dipole moment is just the ampere meter squared. Now, this is analogous to the electric dipole moment, which is just given by the dipole by the P cross E. Right, let us also talk about the potential energy. Now, in terms of the potential energy of the system of the magnetic dipole in the magnetic field depends on the orientation of the dipole in the magnetic field. Now, the potential energy, the magnetic potential energy is just given as minus mu dot B. Now, this is the dot product. And then if you want to write it in terms of the magnitude, you are just going to have a magnitude of the dipole moment and the magnitude of B and the cosine of an angle between them. Now, as a result, the minimum potential energy is just given by this equation, minus mu B. you have to take note of this minus sign, and then this only occurs when the dipole moment is in the same direction as the field, and the maximum is just given by this equation. It must be positive here, and this occurs when the dipole moment are on the opposite direction because of the cosine of theta. Right. I suggest that you draw the cosine of theta in order graph so that you can actually be able to see that this is just going to be the case for the potential, the minimum potential energy and the maximum potential energy, taking into account this negative which comes from the definition of this magnetic potential energy definition. Right, let us just do the following quick quiz. And this quick quiz is just saying that rank the magnitude of the torque according acting on the rectangular loop A, B, and C shown edges on in the figure from highest to the lowest. All loops are identically and carrying the same current. Now, in this case, because the loops are enclosing the same current and the current and they're carrying the same current, the magnitude of the magnetic moment is the same for all, because the magnitude of the magnetic dipole moment is just IA. If the I is the same, the area is the same, therefore it must just be the same. But now mu points upwards for C. Mu points upwards because of that vector area. Therefore, it will just make the it is perpendicular to the magnetic field. Now, if they are perpendicular to the magnetic field, therefore the torque is just given by mu B. The maximum torque possible, this is just going to be the maximum torque possible. I just want to just remind you that the torque is just given by mu cross B. But what is this mu? Mu is just given as I times vector A cross B. Now, this is nothing else, but it's just going to be given as the sign of an angle between them. If I want to get the magnitude of the torque there, this is just going to be a torque. It's just going to give IA, AB the sign of an angle between them. Now, if A is perpendicular to B, like in this C, because this is the loop, that vector area is going to be pointing in that direction. That is going to be my vector area, and the B is coming in that direction. So they are perpendicular to each other. Therefore, the maximum torque is just going to be mu B. The maximum torque is just going to be equals to, that will imply that the magnitude of torque is just mu B, because the sign of 90 is just 1. So this is what is just being said in that case. However, when you look at that, this is just going for the loop in A. For the loop in A, the vector area is pointing in the same direction. Therefore, that is just going to give zero torque. But this is just going to give us the intermediate between 0 and the maximum value, because the A is at a certain angle to the B field. Right, now as a result, this is just going to be the way you will arrange them, because this is the maximum torque and this is just going to be the intermediate, but the A is just going to give us zero torque because of the vector A is in the same direction as the magnetic field B. Right, rank the magnitude of the net force acting on the rectangular loop shown in the figure from highest to the lowest. Now, because the B field is just uniform, therefore there's the magnetic field is uniform, there's a zero net force on all three loops, and this is what we have actually done in the previous example. Right, now let us also talk about the Hall effect. When a current carrying conductor is placed in the magnetic field, a potential difference is generated in the direction perpendicular to both the current and the magnetic field. This phenomenon is known as the Hall effect. It arises from the deflection of charged carriers to one side of the conductor as a result of the magnetic force they experience. Now, the Hall effect gives the information regarding the sign of the charged carriers and the charge density. Now, it can also be used to measure the magnetic fields. Now, in this case, if you have the magnetic field going in that direction and the current is flowing in this direction, now the whole voltage is actually measured perpendicular to both the B field as well as the current. Now the whole voltage is measured between point A and C. Right. With this, good people, I would like to pause there and then see you next time and keep well. Bye bye.